Hello, welcome to CSC 7013 Advanced Math for Computer Scientists. This is Brady Chen. Today, we're going to talk about Module 7, Finite Automata. The theory of automata is a theoretical branch of computer science and mathematics. It is the study of abstract machines and the computation problems that can be solved using these machines. The abstract machine is called the automata. Now here are the learning objectives. We'll first talk about the theory of automata, also known as theory of computation. And then we're going to define a finite automaton. So then we're going to talk about some examples of deterministic finite automata. Automata theory is a theoretical branch of computer science and mathematics. It is the study of abstract machines and the computation problems that can be solved using these machines. Okay, so the abstract machine is called the automata. Okay, now the main motivation behind developing automata theory was to develop methods to describe and analyze the dynamic behavior of the discrete math. Now, these automaton consists of states and a transition. They consist of two things: state and the transitions. Now, normally we use circle to represent a state, and then another circle to represent another state, and another circle. Now, the transition is represented by arrows between circles. Under certain condition, one state, we can state A, can be actually, transferred to another state under certain condition. That's the automaton. So automata is the kind of machine which takes some string as input. Okay, and this input goes through a finite number of states. Okay, goes through finite number of states, and may enter in the final state. Then it terminates at the final state. And we're going to talk about this, in the next couple of slides. Let's first build the models for the automata. Okay, so first we're going to talk about the terminologies used in the automata. So we have three terminologies: symbol, alphabets, and a string. Symbol is just it's the smallest building block. It could be any letter or any symbols like the factorial, pound sign. So this could be a symbol. Here are the examples. A, B, C, 0, 1, any number, or question mark, and factorial. These are all symbols. Now, alphabets are set of symbols. These are sets. Okay. However, these sets are always finite. So for example, we have, the alphabet, which consists of two symbols, 0 and 1. Or we can have 4 symbols, 0, 1, 2, 3, or another 4 symbol set, which are A, B, C, and D. Now alphabets are typically use Greek letter sigma, the to represent. Now the number of symbols in alphabet sigma is denoted by sigma, and we use 2 bars around. We know that the number of symbols in a set is called the cardinality of the set. So it is the cardinality of the sigma. Okay. Now string is a finite sequence of symbols. So once you define the symbol and define the alphabet, which is a set of symbols, and then we can use the symbols in the set to create a string. Okay. So that string is a finite sequence of symbols from some alphabet, and the string is generally denoted as W. Okay. And the length of string typically use this notation. It's the same as the number of symbols. We put the 2 bars on both sides. Okay. Now, for example, we can use W to represent a string 10010. Okay. So these strings are created by the symbols from the alphabet 0 and 1. Okay. So what is the length of this string? W. 1, 2, 3, 4, 5, right? So it contains 5 symbols. So the length of the string is 5. Okay. A string which contains no symbol is called empty string, and typically we use also epsilon. We use that one to represent the empty symbol. Here are some more terms used in the automata. Okay. Now sigma star. Okay. Remember, sigma is a set of symbols. Okay. It's alphabet. So now sigma star is a set of all possible strings over the alphabet. So now, for example, if the sigma equals the set which contains A and B, so it's a set of 2 symbols, A and B. And then what is a sigma star? Sigma star contains, of course, it's a possible strings over the alphabet. So A is the element of sigma star, B is, and then you use the A twice, and then combination of A and B and B and A and B and B, A, so A, B. So it's all the possible strings over the alphabet. So you can repeat the A as many times as you want, and then repeat the B as many times as you want, or repeat the combinations of A and B. Okay. So even though sigma, the alphabet sigma, is a finite set, however, sigma star is an infinite set, because it can be actually, you can continue to actually build as many symbols as you want. So the string could be of any size. So another example is like if you have a sigma which contains only one element A. Now what is a sigma star? Sigma star, of course, it should contain epsilon, which is the empty string. Okay, always include the empty string in the sigma star. And then you have A and A and A. So you can continue to build this. Okay, so that's sigma star. Now the other terminology we're going to use in the automata is called language. So a language is a set of strings. okay, chosen from some sigma stars. Okay, so language is a subset of sigma star, right? It's just selected the strings from the sigma star. Okay, the language could be finite or could be infinity, depend on um, how many combinations we want to use in the stream. Okay. Now the last term we're going to use is called powers of sigma. You know, we use the notation we're going to use is sigma to the n. That's the power n. You know, it's sigma n is the set of all strings over sigma of length n. Okay, sigma star is actually all the possible strings. It could be of any length, but sigma to the n, the power of sigma, it's a set of all strings over sigma of length n. So sigma n is finite. Okay, so let's say, suppose if the sigma is, let's say a and b. Now what is the sigma? Let's say if n is 2 or 3, let's say m is 3, let's say sigma 3, right? So that means it's a set of all strings over sigma of length 3. Okay, so what is this? So we have a, right? So that's a string of length 3. A, B, right? Because you have two symbols. A, B, A, or let's actually follow the order A, B, A, and A, B, B. And the B, A, B, A, B, 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 A, B, B, B. I think that's pretty much all the combination of A and B with length 3. So how many items we have? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so sigma 3 contains 8 symbols. No, I'm sorry, not 8 symbols. Contains 8 elements. Now each element is a string of length 3. So, okay, here are some examples. Let L be a language which consists of all strings of length 2 generated over the alphabet sigma, which contains 2 elements, A and B. Remember, language could be a subset of sigma star, any subset of sigma star. Of course, the strings of length 2 is a subset of sigma star. Then we know that we can generate the L that way, create a string of 2 elements, so AA, AB, BA, and BB. That's all the combination of A and B of length 2. So from here, we can see that the number of strings equals 4. That's not an accident, because if L sigma is sigma contains 2 elements, and the language consists of all the strings of length 2, so then we will find out that the number of strings in the language L is sigma to the 2, so which is 4. Sigma, that's 2. Now, here are some other examples of languages. So let's say the language of all strings over the sigma, which is also contains A and B, which contains AB as a subword. Now this is different from the previous example. So now, which string contains AB as a subword? Let's see. We used L again. Also, we used L, right? So, of course, AB itself contains the subword AB, right? And then we can say A, AB. Is that right? And B, AB. So each string contains the subword AB. And then A, AB, A, B, AB. Well, it contains the AB twice, but that's fine. You just say in a string that contains the subword AB. BA, AB, right? It contains AB. And BB, AB. Or you can say AB, A, which contains A, and AB, B, which contains AB as a subword. So you can create any string A, B, 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 A, as you know, A, as far as it contains AB. So how many elements contained in the language? It's clear that this language contains infinite number of strings, right? Because you can always create a string which contains AB. As far as it contains AB, then that's part of the language. Okay, so that's the second example. Okay. Here, I'm not going to spend much time on this, but I gave you some time to work on this. So let's create a language which contains all strings over sigma. Now the sigma contains two actually alphabet, 0 and 1. That ends with 0. So you can create a string of binary numbers 0 and 1. It doesn't matter what the string is, but that string must end with 0. Okay. Think about this. Again, think about the number of strings in that language, right? Okay. Let's stop over here. Now let's actually talk about two properties of the automata. Okay. So the first proposition 1, says for alphabet sigma, which contains two elements, A and B. Now with length n, the number of strings can be generated is 2 to the n. Okay, so that's one. The proposition 2, the number of strings of length n, possibly over sigma, is the number of elements in the sigma to the n. Now, let's actually take a look at some examples to illustrate this. Now, the first one, because the number, sigma contains two elements. Okay. Now, if you want to generate a the strings of length, say length 2, we know that from the previous slide that the total number of elements could be generated is 4, right? So if n equals 2, then with two elements a and b, you can generate AA, AB, BA, and BB, right? Now what about n equals 3? Now you can generate a string of length 3. So that's the combination of 3 AA, that's 1, right? AAB, that's the second one. ABA, ABB, and the BAA. You try all the possible actually string of length 3 using A and B. Okay. Then BAB, that's the next one. BBA and BBB. How many of them? 1, 2, 3, 4, 5, 6, 7, 8. So this is more like a combinatorics problem in math. So you have certain number of elements, and you want to actually generate the combination of these elements of length 3 or length 4, you know. So now in general, let's talk about n, right? So for n equals 2, you know that the sigma contains 2 elements. So the cardinality for sigma is 2, right? So then the language we can generate with n equals 2 is 2 square, which is 4. Now here, next one, n equals 3, sigma is still 2, and the language we can generate is 2 to the 3, 8. So then we can assume that for general n, the number of strings can be generated is 2 to the n. Okay, so if we have if we want to generate a string of length 10, then it's going to be 2 to the 10, which is, I think it's 1024 elements. So it could be A 10 A's and A B, a 9A and a 1B. So you can actually create all the combinations of A and B of length 10. So now proposition 2 is slightly different. Now in that case, you know, if let's say sigma contains 3 elements, A, B, and a C. Now we want to generate a language of length, for example, length 2. Okay, so then you can say, okay, for 3 elements, if we want to generate a strings of length 2, now how many strings we can generate? Okay, now based on this proposition, we know that it's going to be sigma to the n. Now sigma contains 3 actually alphabets, so we can say it's a 3 to the 2, that's 9, 3 square. Now let's see how can we generate these 9 strings. Okay, it's a length 2, right? So let's say AA, right? Okay, so we can actually generate this with certain order. So we first actually create the A, okay? Then first the AA, and then AB, right? A and B, and then AC, right? So then we put the B first, B, then BA, BB, BC, right? And then CA, CB, and the CC. So we have total of 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 3 to the 2, that's 9. It's 3 square. So now, with all the terminations and the definitions, such as the languages, and we are ready to define a finite automata, or we use FA. Finite automata, or sometimes we call the finite state machine, is a simple idealized machine used to recognize patterns within input taken from some character set, which we use alphabet or sigma. Now the job of the FA, the finite automata, is to accept or reject an input depending on whether the pattern defined by the FA occurs in the input. Now let's take it another way. Think about a language. Remember the language we define, right? For example, if we have an alphabet sigma, so say sigma contains two elements, 0 and 1. And then we define a language which meets certain criteria. For example, one example is the language contains all the strings from sigma of length 2, all the strings of length 2 from sigma. Or the language can be defined as all the strings which contains 0 at the end, right? That's another example we just talked about. So a language is certain, string, could be infinity or could be finite. So now the purpose for the finite automata is to, check if someone gave you a string, say 011101. Okay, now this can be served as an input, okay, to the finite automata. Okay, so this is an input. Now we need to build a finite automata to check whether that string satisfies the criteria, or whether that string is part of the language L. So then we end up that the finite automata eventually going to end up with the conclusion, say, well, we accept that string, or we reject that string. If the string is actually part of the language, then we accept the string. If the string does not meet the criteria for the language and it's not part of the language, then we reject. That's the purpose for finite automata. So finite automata is an abstract machine which have 5 elements. We're going to define these 5 elements, or 5 tuple. Okay, it's the same thing. Now it has a set of states. Okay, we're going to define in the finite automata a set of states and the rules for moving from one state to another. Okay, and then depend on the applied import symbol, we're going to the finite automata going to based on these states and the rule, we eventually say we accept this import, we reject the import. So it's basically an abstract model of digital computer, right? Now think about a computer language like Java or Python. Now the language has to meet certain criteria, right? Like L, we say define L, which is Java. Of course, these language like Python, Java is more complicated than the language we talk about here. So the criteria is much simpler here than Java or Python. However, the concept is the same. And then when people actually write statements, and then we can check that statements meet the criteria of the language. So think about this is like a compiler, right? So the compiler going to accept this import, and then it's going to actually accept these import or generate an error message to say, no, that's not the Python language, does not meet the criteria, does not meet the syntax for the Python. It's just like this concept, okay?